Perfect. Hello all. Welcome to this super SPH group meeting. For those people who don't know me, I am Chun Hean Lee from University of Glasgow, senior lecturer at the Glasgow Computational Engineering Center. And today I'll be chairing this session, this group meeting. And in this hour, we are going to have two very interesting presentations. They are all related to SPH and related to the layouts of the program today. We are going to have 20 minutes for speakers and then another 20 minutes for the second presentations, and then followed by 20 minutes for question and answers. So the first speaker, I would like to welcome the first speaker, Dr. Bastien from Fraunhofer Institute of Mechanics of Materials.
Yep.
Yeah, let's pass it over to you.
Thank you. I will start sharing once I select the correct screen. I hope. Let me just see. Okay, good. Go away. So good morning or good afternoon, everybody. Maybe one word about Fraunhofer for the Chinese colleagues, because Fraunhofer is kind of like, it's not a university, it's a research institute, which has a special focus on industrial application. That means we do research similar to universities, but there's a need that there needs to be like an industrial customer behind it. So maybe that will explain some of the content that I'm going to present. So today I'm going to talk about SPH, of course, but with respect to a special process, which is the laser powder bed fusion. So laser powder bed fusion, for those who don't know this process, is thankfully pretty easy to explain. We do have powder. We have this roller. The roller makes a nice smooth surface. Then we have the energy source. So that's the laser. The laser hits the powder. The powder melts, the powder solidifies. So this is what we get, the printed part. However, the story does not end here because typically industry has like many further questions, which are, for example, what is the porosity? What is the corrosion behavior? The life expectancy? So features that are far beyond of what you can see. So of course, the hope is, can we use numerical simulation somehow to address those features? So this is what we try, basically because the process itself is pretty complex. We use a sequence of simulations. So basically what we do is we use the discrete element method for the powder spreading. We use the melt pool. We model the melt pool dynamics using SPH. So this is going to be the content of today. And then we move on to use a cellular automaton to predict the microstructure in this printed part. And we then use this microstructure for mechanical properties. So this is going then to be an FEM simulation. But as I said, today is SPH. SPH in the whole sequence, in my opinion, is more like of the more complex steps, simply because of all the physics that is involved in this melt pool dynamics. So just to give you an idea, we have so many things to consider. There's the laser. The laser is being consistent of multiple rays. So these rays are going to be reflected. The rays are going to be reflected deep into the powder bed. We do have absorption. We do have phenomena such as heat conduction, heat transfer. The powder is going to melt. The powder is going to solidify. We have lack of fusion. So you see there are many keywords on this slide. So there's a lot of physics being involved here. So the question is, how do we model these? So one method, so it's not the only one, but one method is SPH, which we like for this one, simply because when you see on this slide, you see all those surface area. And we know SPH, when it comes to surface area, is really the game changer. So let me see. We have all those. Can I remove these? I don't know if you see these. How do we model all of these? Let me come to the balances in SPH. So mass balance is pretty straightforward, simply the continuity equation or incompressibility. So this is easy. Momentum balance, we do use the pressure. So this is like common. We have the viscous force. This is also common. We do have gravity. but we also need to include surface tension and recoil, and I will come to it in a couple of slides to tell you why. Viscosity is temperature dependent, so this is simply stated here. It depends on the state of matter, if it's like liquid or solid. So if it's solid, it should not move. If it's like liquid, it has like a Newtonian liquid viscosity. But if it's like in this transition behavior, there is simply kind of like an interpolation in between, but it depends on temperature. What also depends on temperature is, I'm on next slide, is the surface tension. So surface tension has two contributions. It's normal tension and tangential tension, also depending on temperature, and I will tell you why in a second. Similarly, for the recoil pressure, for those who had thermodynamics, you will spot this Clausius-Clapeyron equation, which also depends on temperature, but with an exponential function. So temperature here is like really affecting the surface tension a lot, the recoil pressure a lot. Laser intensity basically is a Gaussian distribution, and the energy balance is simply the summation of all those contributions. And this is going to be the end of all the equation I'm going to show you. From now on, we do only have videos. So rate of strain, just to finish, and absorption, pretty straightforward. Let me give you a demonstration, like how does it look like? So what we have here is substrate. So this is going to be already molten layers from previous printing steps. And here on the top, you see the powder layer. And this is the laser. And you see the laser traversing the powder melts, the powder solidifies again. And on the left, you see the temperature profile. And on the right, this is the state of matter, meaning like, is it solidified, is it liquid, or is it evaporating, etc. So coming a bit more into the details. So what do we need to consider if we want to model this process? And one of the most important part actually is the heat conduction. Let me explain you why. So what you see here is kind of a powder bed. And what we model is a heat source coming from the right. And you see this is the temperature being color-coded, and you see the temperature gradient being formed. So there is like a heat transfer going from right to left. However, there's a difference with respect to if we compare a powder with the dense material, and this is this figure. So what we're looking at is the heat conduction. So here on top, this is the dense material, fully dense, and here on the bottom, this is the powder. And I want you to see actually that there are two orders of magnitude in between both of them. And this is crucial simply because there's so much air in between, and air acts as an insulator. So that means in the powder bed, if you have like a heat source somewhere, the heat can't dissipate as well as if you have a dense material. And the simulation, thankfully, basically when using SPH, is able to capture those two orders of magnitude. And this is really important because otherwise this is like a large artifact. Coming to the terms where I was talking about, like I will explain you in a couple of seconds, where we need the surface tension and the recoil pressure. Let me just explain you what happens if we don't do so. So here you see a specimen, and there's a laser coming from the top, and we don't see the laser, but this is the temperature profile. So you see, if we do not have temperature dependent surface tension, basically what you see, there's a temperature profile for sure, but you see the matter stays where it is. In contrast, if we include this temperature dependent surface tension, you see matter is being shifted to the right. And this is becoming more significant if we compare purely what we just saw. So this is just what we saw on the previous slide. In comparison, if we use the recoil pressure. So recoil pressure, just to give you an idea, what does it mean? So we have liquid, so we're first solid, then becomes liquid, and the liquid becomes vapor. So when it becomes vapor, of course, it occupies so much more volume, and using more volume, this creates this recoil force. So you see that this force basically pushes the matter, and it looks like it's being burned down into the material. So those two contributions are crucial if we want to have those effects of like this deep hole. Some more details with respect to whoever is interested in model this process. So of course, we were coming from the weakly compressible scheme, and then we gradually moved to the SPH scheme. So just to give you an impression, like what happens if you use one of the other schemes. So left is the weakly compressible, right is the SPH. And I want you to see the spattering here. And this is something that we couldn't get rid of. So it was annoying us because it looked like weird, and basically, you see like this rough surface, and this is not what you saw in the experiment. What you saw in the experiment was kind of like this nice smooth surface. So we know that SPH is creating the nice smooth surface, but basically here it's not like, oh, it looks nice. It was important because you see there's a difference between the two of them, and this is what we see in the experiment. Why they look so different, that's a good question. We don't know. We just fortunately saw, okay, coming from left to right solved our problems. So don't know why. Optics. Optics is not related to SPH, but just to give you an idea what I'm talking about. When I have this incident beam here, the beam is being split into a reflected beam. So that's the surface, so it's being reflected and partially refracted into the material. Optics is also telling us it's going to change direction. We can compute the new direction using Snell's law. It's also going to tell us once we have like a total reflection so that nothing is coming into the material. And we can also compute the amount of energy that is being split. So this is coming from Fresner's equation. It's simply telling us, okay, if we have like so many watt coming in, how many watt are coming out and going into the material. So how do we do this now in the simulation? Pretty straightforward. So this is a 2D example where you see that the laser is being discretized into multiple rays, and each of the rays is simply being modeled individually. And I want you to see this inclusion here. So it's just there for a couple of seconds, but this is, stop the video, please. But this is something that you can also see in the experiment, but we couldn't realize this when using an analytical function, which means like, okay, the laser is simply this Gaussian profile. So using this kind of like laser ray tracing, only then we got those inclusions. This here on the right is simply the same, just in 3D. 3D is so expensive. Let me tell you this. This goes fast. This is a nightmare. Just to tell you. To give you an idea how well does this work, so we were pretty satisfied with what we got. So as I said, we have an experimental partner. They do this in the lab. So this is what they got. I'm not going into all the specification, but if you want to know, I can share the details. So they have this powder bed and they have a size distribution of the powder. We modeled this in the numerics, and this is then how it looks like in the simulation. So you see one single track in 3D. So now I want to go more into the video and fun part. So what you see here is kind of like the top view. So it's the same powder that we just saw in small. So this is the height profile color coded, the same state of matter and the temperature. And you see, or you don't see, but there's the laser coming from left to right. And you see there's a blue spot here. The blue means here, this is deep. So basically, see here, there is a hole. Why here, this is like the top layer. Why am I telling this? Simply because we can now do funny things, such as like we imagine we are put on our X-ray glasses. So this is kind of like the side view where you see the whole top view or the back view. But what I want to mention is we see this hole. So keep in mind this hole because now we start to do a parameter study. So on the left, the very same, but we have a really slow laser, the same amount of energy. So you see there is like a large intense blue color, so deep hole. So if we fasten up the laser, there's less blue. If we go faster, you see even less blue. So again, we do our X-ray trick. So you see a deep hole, you see less deep hole, and almost no hole again. So now I want to stop for a second and ask you, like, what do we actually want? So, I mean, it's cool to look at those holes, but what is the person operating this process actually looking at? So what we want is that this top layer of powder, this is supposed to be fused together with the substrate. If we have the deep hole as on the left example here, this is not what we want because we get these inclusions. Inclusions, that means porosity, Porosity means less dense, and this will rather lead to corrosion, to failure, to reduction in life expectancy. So basically what people want is this right one. This is called the conduction mode, so simply because it's possible for the material to convey all the energy to the sites. And this is where we're saying, you remember powder bed and has problems to convey all the energy. This is where it's becoming important, because basically we want to know how much energy can we put into this so that it's not producing this deep hole here. So just nice images, because people also did the very same in a synchrotron. So basically they put it into, you can imagine, a gigantic X-ray machine. So they can really see into the experiment. And this is where it's becoming cool, because you see simulation and experiment look similarly for both. And this is something that we only saw for SPH, not for this finite element method. So basically, this is what we're saying. Yeah, SPH has a point, because this you can do. The others, with the other method, we didn't see. Maybe it's possible, but we didn't see so. Okay, details on the numbers I'm going to skip. And then I'm running out of time, but it's just 2 slides. Last but not least, porosity. Porosity is important for material properties. You see powder here, and you see that here it has been molten. So we're interested, how strong is it porous? Basically, what we do in the simulation is we add powder, we melt it, we add powder, we melt it, and again, and again, and again. Weak laser on the left, becoming more on the right. So you see here, this is really porous, less porous, seems like almost dense. So if we compare this now with the experiment, so this is different parameter study, different laser velocities, different laser intensities. The black one is the simulation, the green one is the experiment. But what I want you, so I don't want to look at the numbers, I want you to see the trend basically works pretty well. So this is again like, okay, SPH can really be used for this process to understand or to predict. I don't want to say predict, but to like get an idea on how the porosity is going to evolve. So this is going to be the end. What we would then do, but it's not topic of today, use this information for the next sequence in order to predict the microstructure, and then use these information for the mechanical properties. But I hope you agree that this map-pool dynamic with SPH is pretty complex, but can be done. With that, I'm ending my talk. So the simulation you saw were done in using our in-house software, Sympathics, but it's basic SPH code. And of course, what I was presenting today was the contribution of many other, as well as many funding agencies and projects. With that, I'm ending, and I thank you for your attention.
Right. Thanks, Bastien, for the very, very interesting talk. Yeah,
You're welcome.
To show the advantages of SPH in the application of laser powder bed fusion. Very interesting. Let's move on to the second speaker. Daniel, you there? Yeah, perfect. So I'll pass it over to you, Daniel. You have
Just sharing my screen. All right, so you can see all my slides now?
Yes, I could, yeah.
All right.
Perfect.
Okay, so first of all, I want to thank the organizers for giving me the opportunity to present here at the SPH Supergroup meeting. And I want now to jump from the simulation of powder bed fusion to a very similar process to the simulation of laser beam welding. I want to start with a quick motivation. So during laser beam welding, pieces of metal are getting joined in a molten state by the use of laser beam. And usually we have evaporation temperature on the surface, which leads also to a vapor-filled capillary within the melt pool. The process is very popular in industry due to several advantages. So we have a narrow heat affected zone with low thermal distortion. We have a high welding speed and as well high flexibility. Here on the bottom right, you can see an X-ray video of a real laser beam welding process of aluminium. And what we can see is that the process easily becomes unstable and weld imperfections may occur. For example, here the formation of process pores in the back of the weld pool. Also, when you have a look at this X-ray, you can imagine that the experimental observations are very limited due to inaccessibility. And so that's the reason why I perform numerical simulations to understand all the physical effects that lead to those instabilities and to further optimize the process. Okay, so when you now want to simulate the process, a lot of physical effects must be included. So for example, we have the laser material interaction. So we need to consider multiple reflections on the material surface. Then we have heat transfer by conduction, convection, and radiation. For the solid phase, we need to consider thermal stresses and distortion. For the liquid phase, we need to consider fluid dynamic effects such as surface tension, Marangoni convection, and wetting. Then we need also to consider phase transitions between the phases. And last but not least, we have also temperature-dependent material parameters that lead also to thermal expansion and contraction of the material. So how do we tackle or how do we simulate the process? We simulate it by using the SPH simulation for the fluid and thermodynamics. And on the other side, we use a ray tracing approach to consider the laser material interaction. How do we couple those two domains? First, we detect the surface particles in the SPH simulation. Then we reconstruct the surface capillary, send this as an input to the ray tracer. The ray tracer then calculates the absorbed intensity distribution on the material surface, sends this back to the SPH simulation, where the intensities gets transformed into local heat source particles. Okay, so let us now have a closer look on the SPH side of the simulation. So as you all know, SPH is a scheme to transform partial differential equations in time and space into ordinary differential equations in time only. And by doing that, we can transform our governing equations, basically the continuity equation, the momentum equation, and the energy equation, into an SPH formulation. And here I want to highlight some terms. So basically in the momentum equation, we need to consider a pressure force, a viscous force, and a surface and gravitational force. While in the energy equation, we have a heat conduction term, as well as a heat source term to consider the energy input of the laser beam. Then I also want to mention that we use the weakly compressible SPH method, with a stiff equation of state, as can be seen here in the bottom of the slide. And we use a temperature-dependent reference density in order to account for thermal expansion and contraction of the material. For the solid phase, the equations look very similar. So basically, we have the only difference in the momentum equation, where we now use the Cauchy stress tensor. And for the deviatoric part of the Cauchy stress tensor, we apply the updated Lagrangian method. Now I come to the surface model. As mentioned also before, the surface model is very important since the process is dominated also by surface tension and recoil pressure effects. We apply for the surface model the continuum surface force model of Bragg-Will. And in our surface force, we consider three terms. The first term basically includes the surface tension, including wetting, as can be seen here in the droplet collision of two droplets, or in the wetting behavior of a liquid droplet on a solid plate. Then the second term describes the Marangoni convection, so basically the flow from low surface tension to high surface tension, which means for metals from hot surface to cold surface. And the last term is the recoil pressure, which gets induced by the expanding evaporated material on the liquid surface. Okay, so now we have seen the SPH side of the simulation. I also want to spend a slide for the ray tracing scheme. So as mentioned before, the ray tracer takes as an input the surface geometry as well as the temperature data, as well as beam and tracing parameters. Then we represent our laser intensity distribution by thousands of rays. And for each ray, we calculate its propagation. Then we check if the ray is penetrating the surface. If yes, we identify a triangle and calculate the absorbed intensity on the triangle. Then we repeat this procedure for every reflection and for each ray. And when we have done this, we can sum up all the intensities of each triangle and send this information back to our SPH simulation. Okay, so then we come to the simulation results. Here on this animation, you can see the deep penetration laser beam welding process of aluminum. And to summarize the physical effects, we have a laser material interaction using a ray tracer. We have for the solid phase thermoelastic material behavior. For the liquid phase, temperature-dependent surface tension, including wetting. We have heat transfer by heat conduction. For the phase transitions, we apply the enthalpy method, which also considers the latent heat of fusion and evaporation. Then we have an evaporation-induced recoil pressure. And last but not least, we also consider thermal expansion and contraction of the material. To validate our model, we compare the experimental observation with the simulation results with experimental observations. And basically what we can see here is some X-ray images which are showing the melt pool size and the capillary shape in the experiment. And what we can see is that both parameters agree very well. We also have conducted a small convergence study where we can see that we converge with increasing particle resolution to the capillary depth observed in the experiments. What I want also to mention here is that we need a certain particle resolution in order to have like a certain amount of particles under my laser beam. Otherwise, we cannot simulate the process accurately. Okay, so now we have seen that we can simulate the process using our simulation model. Now I want to apply also the model to 4 applications. First of all, I want to present some adaptivity and boundary conditions which aim at reducing the simulation time. Then I want to present the influence of laser beam scattering. I want to present the welding of dissimilar metals, and last, the influence of the ambient gas. So as mentioned before, the goal of the adaptivity and boundary conditions is to increase the numerical efficiency. So here we have a look at the process of the conduction mode welding process, which means that we only have surface melt pool and also a shallow weld seam. So in order now to simulate the process very accurately, we would require to represent the whole workpiece and use adiabatic boundary conditions to represent the thermal properties exactly. But that would lead to very high computational times. So what we can do is that we can say at a certain depth there will be room temperature, and basically we can apply a Dirichlet boundary condition. We can even further reduce the amount of particles by applying a Robin boundary conditions, which assumes that a certain distance from our lowest particle level will be room temperature. The second thing is to apply multi-level particle refinement and coarsening. So basically we can dynamically split and merge particles during the simulation in order to ensure a fine particle resolution in areas of interest. Third thing is that we also can use the symmetric boundary or symmetric boundary condition. So basically we can reduce the amount of particles by a half, and we need to introduce mirror particles close to the symmetry boundary in order to fill the truncated kernel support. Last is something what we call particle influx and deletion. So basically what we do there, what we mean with that, is that we create particles in front of the laser beam, and as soon as they have reached the back where no special physics happen anymore, we delete them again. Okay, so let us have a look on the simulation results. And what we can see is that we have in each simulation the formation of a very shallow melt pool. And also the size and temperature distribution agree very well for each simulation. So let us now have a look on the simulation time. And for the first, we have very high computational times. And what we can see is that by applying adaptivity schemes or even by combining the third and the fourth approach, we can reduce the simulation time by a lot. So the key message is here that there is a high potential to increase computational efficiency by focusing on the area of interest, which is in our case, the melt pool dynamics. So now I come to the second application example, the influence of the laser beam scattering. So what we do here, normally we assume for our ray tracing approach and reflection on an ideal smooth surface. What we can now examine, we can examine surface scattering due to fine surface structures on the surface, or even volume scattering due to condensed droplets within the capillary. How do we model those two effects? We model surface scattering by assuming a diffuse reflection of the laser beam on the capillary surface. So therefore, we just need to define a random surface normal. Volume scattering is a bit more complicated. Here we need to define two things. First of all, we need to calculate or determine a distance which our ray needs to travel or propagate to our next scattering event. And when we know the scattering event, we also need to define a scattering angle at which our ray gets deflected. For the scattering angle, we apply the Henry-Greenstein model, which basically defines the probability function for the scattering angle. Okay, so let us now have again look on the simulation results. On the left, the simulation with no scattering, and on the right with only volume scattering. And what we can see is that the capillary depth in the simulation with volume scattering is almost constant. So this we can see even better here on this slide. So without scattering, we see or observe the formation of melt bridges in the simulation, where basically the back of our capillary unites with the front due to high surface tension forces. And that leads also to a strong variation in the total absorbed power. For volume scattering, we can observe that the absorbed power is better distributed, and that results in an almost constant depth of the capillary and also into a highly increased capillary stability. On this slide, we can see the mean and standard deviation of the capillary depth, and we can see that both scattering events don't or have a minor impact on the mean depth. And for surface scattering, we still observe those high depth fluctuations, while for volume scattering, we see that we have an increase of capillary stability. The key message is here that there is a strong influence of the absorbed intensity distribution on the capillary stability. Now I jump to my first simulation example, the welding of dissimilar metals. Here in the example of aluminium over copper. And basically here is the goal to minimize the inhomogeneous phase between aluminium and copper. And usually in the experiments, what is done is that you can apply an oscillation of a laser beam, which then reduces highly the creation of this inhomogeneous phase. Okay, here again the simulation results. For on the left side, you can see the simulation with a low amplitude of 0.25, while on the right it's a high amplitude of 0.75. And what we can see is that the amount of used copper is on the left very high, while on the right it's very low. And also on the right, we have like the existence of almost 2 capillaries in the simulation. And we now compare the simulation results of the experiment. We can see that the fused areas of aluminum and copper are in very good agreement. Now I come to my last simulation example, the simulation or including ambient gas. And here's the challenge to include also the high density ratio between the workpiece and the ambient gas. How do we tackle it? We tackle it by applying the Riemann SPH method, where we basically introduce a one-dimensional Riemann problem between interacting particles. And then we need to change our governing equation slightly by introducing an intermediate state. And this intermediate state we solve by using the Roes approximate Riemann solver. Okay, so again, some simulation results. here including the ambient gas. And what we can see is that the ambient gas is flowing inside the melt pool, and that we also observe a very complex flow behavior of the ambient gas. Okay, let us have a look on a typical sequence in the simulation. And that looks something like that. So typically we have the formation of a narrow capillary. Then it comes to a constriction at the upper end due to high surface tension forces. We can see the separation of the process pore in the simulation. Then we have the reformation of a narrow capillary due to high recoil pressure forces. And then we have the deflation of the pore into the capillary. So basically the result is here that we have the formation of temporary pores due to alternating capillary expansion due to recoil pressure, as well as capillary collapse due to surface tension. And these results are also in good agreement with experimental and numerical results. So now I come to my end of the presentation. And what we learned so far is that laser beam welding is a joining technique involving several important physical effects. And we need to include all of these effects to being able to simulate the process. Then we have also seen that the SPH method is well suited for the simulation of the welding process and is also able to capture the rapidly changing free surface and liquid-solid interface. And we can also capture the main characteristics like melt bridges and the formation of temporary pores in the simulation. And for future work, we also want to investigate the influence of further process parameters on the process stability. And we also want to further extend or improve our model by also including the vapor phase. So not only the ambient gas, but also the vapor phase in the simulation, as well as the influence of condensation of the vapor phase within the capillary. So that's the end of my presentation. I want to thank you all for your attention.
Right. Thanks again, Daniel. Again, another very, very interesting talk regarding SPH. So now we move to the last bit, which is 20 minutes. Then basically it's open for any questions that you want to ask related to those two presentations. And so either you turn on your video and you ask the question, or you could leave the question on the chat and I'll try to read it out for you. Right. Any question for the audience?
Maybe meanwhile I bridge because I have some questions. Daniel, thanks. It's super interesting. I talk until somebody's raising the hand. Daniel, you said you're using thousands of rays to discretize. We use 100. Why do you use thousands? Because the laser ray tracing is so expensive. Did you do like the studies to say, well, I need so many, or?
Yeah, okay, we use thousands of rays, but we don't apply the ray tracing scheme at every time step in the simulation. So what we do is that we say, okay, during our weekly compressible simulation, we have very small time steps. And during those time steps, our particles hardly move. So we are not, it's not necessary basically to apply this expensive ray tracing scheme every time step. Okay. So basically we define a time interval where we just apply the ray tracing scheme. And this allows us to also use more rays and being from this side more accurate.
Okay, thanks. For the volume scattering, I was curious, when I get it right, it's because you say there's vapor, and because of the vapor, there is kind of like the scattering. Yeah. But is the scheme somehow, so I never thought about it, is the scheme somehow like estimating the amount of vapor particles in the air because of the process history, or how does it work?
Basically, yeah, we just wanted to examine like the influence of those two physical effects, but it's hard to say like if there are any vapor particles, or if there is something inside the capillary which also reflects our ray, and if yes, how hard or how great will be this effect of those things. What we did in the simulation is just that we assumed and tried out, okay, how it looks like if we have those effects and how would they influence the simulation. And I guess the most important thing from the results is that this complex intensity distribution, like which is influenced by this scattering effects, have a great influence on the simulation and on the capillary shape. That's one nice thing. Yeah.
Okay, thank you. I see there's a question, so I hand over.
Perfect. All right, Sam, you go on.
Okay, thank you for the chance. I actually have a question to both of you, because both of you may already mention that the ray tracing part is quite expensive. Because as I know, SPH itself is quite expensive. So you say ray tracing is more expensive. So what is the possible reason why make it the ray tracing so expensive?
Maybe I start.
Perfect.
Basically, it's easy. This is already like coming out of the discussion of why Daniel is using thousands of rays. So you have to imagine for each of the rays, you have to like propagate and inspect. Do I meet a surface particle somewhere? So meet a surface, no. Oh, there's a surface particle. Then compute the new angle and then propagate further. And every propagation steps, like, do I meet a new SPH particle? No, yes. No. So it's basically propagating every particle and then estimating, okay, imagine my powder bed, it's going deep into the powder bed. It's just a complex projection.
So basically, is this the same ray tracing technique in the rendering industry, or when people do the animation, they do the same way?
I don't know. I think they are more clever than us, I guess, because they don't care about accuracy. For them, it just needs to be fast. So I don't know, but I would say they do it more like, I don't care, and it should just work. And if it looks good, it's theirs will be so much faster.
Okay, so another way is that means from your descriptions, more like the ray tracing is something like the DEM approach. Then they need to meet, they need to trace the direction, and if they meet someone, then reflect back.
Yeah. So the point is, if you turn on this laser ray tracing, there's also like your you know, how often do you check if you meet a particle surface? So there are like kind of parameters that you might be able to fine tune to fasten up. So as we don't know, we're like pretty safe and like scan too often. So it might be improved and further. The point is, like, if you don't do so, you don't get those effects that Daniel and me were showing and which we see in the experiment. So it's kind of like, we have to turn it on. And industry is also asking for it, even though they don't know how much more computational load you put onto it. Everybody's asking, oh, do you turn on the laser ray tracing? Okay.
Okay. So it seems like you guys do this later work is use a similar approach. Daniel use a similar approach with Bastien, or?
It's actually very similar. I guess we have one additional step where we also need to reconstruct the surface mesh. So basically we give like a triangle mesh as an input for our ray tracing approach. But the other things...
my question also, yeah. So you mentioned you use triangular mesh.
Yeah.
So that means you need to build up a mesh from a particle simulation.
Yes, exactly.
That's make it even more expensive.
That makes it even more expensive. Yeah, so we need to first detect our surface particles, then we need to reconstruct it. Then we have also like a ball pivoting algorithm which we apply, and yeah, it makes it even more expensive actually.
So from Bastien, how you avoid this difficulty? Do you don't use triangle, or you build up this triangle mesh for the tracing, or not?
No, we don't use the triangle, but in contrast to Daniel, you know, Daniel fixed it once. So he computes the expensive triangle mesh once and then keeps it constant. So we do this computation every time. So I guess in the end, it turns out to be like the same amount of time that we waste. I would call it waste.
So you don't build up the triangles.
No, but it's similar. Like we inspect, do we meet an SPH particles, and then if we say, well, there is a, let's say, collision with an SPH particle. Similarly, still we have to know the surface. So we know the normal because it's already in the scheme, but then we know the normal, and then we somehow like basically it's not a triangulation, but it will turn out the same computation in the end.
Okay. Yeah. That's why I heard you guys say this 3D is nightmare. Yeah. Okay, thank you. So I stop here. Okay.
Thank you. Any other questions?
may I ask a question?
Yep.
Bastien?
Yeah, please.
A simple question. I'm wondering because you have a different size of powder. So how you generate these particles for this different size of powders?
Yeah. The advantage is that we can take advantage of the proceeding discrete element method, because in discrete element method, each powder particle is one particle. So they have a different size. You can say you're one particle and you have a radius of whatsoever. And then there's another one that has a radius of whatsoever. So we just like let them fall and distribute, because this is like one, you can imagine like Newtonian dynamics. It's just spheres, marbles that you have like in a ball and you shake it. So they will rearrange that goes super fast. So that is really like tuck and you got it. And then what we do is we take this, let's say, gigantic DEM particle and replace it by tiny SPH particles. So in the end, these are on a lattice and we just cut them out so that they become a sphere, which before was the DEM particle. So this is how we discretize the big DEM into this tiny SPH, like a lot of tiny SPH particles.
Yeah, okay. So for one not just the powder, how many SPH particles inside?
Now that's the difficult question. Let me start. Usually industry is saying like, those powder particles, they are roughly like 40 micrometer in size. So before we said like, okay, let's do like 5 micrometers. So at least that we do have like a certain discretization. And now they say, oh, if we observe, if we use fine particles, like fine powders, let's say like 5 micrometer, it becomes even better. So can you please do this? But using, if they reduce the size of the powder particles by a factor of like 3, we also need to reduce the SPH particles by a factor of 3. So, if you have 3D and you like reduce the size, the number of SPH particles is bam. So, patient is the answer to your question.
Okay. Okay, thank you.
All right. Thanks, Dong. Any other questions? If not, I got a couple. Let's
Yeah,
go for the
please.
first one. So actually for both speakers. So in your simulation, it seems like, well, it's very interesting that you have like a temperature shock. So basically you got a massive temperature variation in a very, very short dimensions.
Yep.
When you do the SPH, do you need any other treatment, or will you encounter some non-physical temperature instability, things like that, or it just works fine when you do SPH?
I let Daniel start and then I comment, because I'm afraid I talk too much.
Yeah, actually it works fine. We have maybe, depending on the material, we get some problem. For example, when we simulate steel, is that we have a very low heat conductivity for steel. So what we observe there is that the melt pool layer at the front of the capillary is very thin. And to resolve this, we would also require like a very fine particle resolution. And this makes it a bit hard because the simulations time are very long and we cannot go with those very fine particles, which makes it hard, especially for a simulation of steel.
Perfect.
But yeah, the rest, I would guess it's okay.
Yeah. What about Bastien?
Yeah, let me continue. Remember when I was saying we started with weakly compressible and went to ISP? So the problem is the following. As you said, there's really high temperature. So then there is this exponential of something with a really high temperature. So the surface, this recoil pressure is enormous. So whatever kind of dynamics you have in your system, they don't matter, because the recoil pressure at that point will simply erase the particle, will just like flow out of the simulation volume and it's gone. So basically what will happen is the number of particles during the simulation just like decreases and everything is gone. Moving to the ISPH, that worked finally. So the ISPH scheme somehow like doesn't care, just push them back so that it's a nice method. So ISPH solved this issue. But yes, the high temperature.
Okay, so there is a slightly issue for this weakly compressible aspect.
For weakly compressible, I would say
you
can't deal with this.
Okay.
Yeah.
Well,
yeah, maybe I can also add a small comment to that. So we also need to add like certain correction schemes in weakly compressible SPH, like delta SPH, and also amount of artificial viscosity to deal exactly with the problems. which Bastien mentioned. Yeah.
Okay, perfect. All right, thank you. Xiangyu.
Okay, thank you for the chance. I will still have more questions. So, because you say you guys both maybe you both have a temperature dependent viscosity or something like that. So I'm wondering when you reach the range of infinite viscosity. So what you did, you just stop there moving, or what are you doing for the infinite viscosity?
Yeah, maybe I start. Basically, we have an implicit solver which does exactly this. So basically the number is not infinite, but it's pretty high, and the result of it, like they stop moving. So it doesn't matter what happens, they stop moving, but the ISPH scheme is still allowed to rearrange them. So it's still saying please stop, but the ISPH scheme say like, but there it would be better if you were here. So but yes, so it's not fixed that it say like in the solver if then don't move. ISPH can still move them, but the result is movement is like gone.
Okay, so you basically still need a because implicit means you need a reinverse a big matrix to stop this.
Yeah.
Daniel do the same thing, or you use a very different approach?
We do it a bit different. So we can choose if you want to also simulate the solid material as an elastic body. So therefore we use then basically the elastic formulation, SPH formulation, or we could only say that we just fix those particles in the simulation. So when we don't use elastic formulation, we can just fix them. And as soon as they are getting molten, we just transform or just unfix them, and then they belong to the liquid phase.
Okay, so now that make me a question about gravity. When you do a simulation, do you really apply gravity to the particles, or you are not applying it?
Let's say gravity doesn't take too much of an issue in this process. The gravity doesn't matter. It's the surface tension that moves the particle. It's the recoil pressure in my case. I guess for Dane, it's going to be the same. So if you turn it on, so of course, if you just turn it on, you know, it will just fall down because you don't have like a ground. It will just start moving downwards. Gravity is not an issue. So you just turn it off for the sake of making it easy.
Okay, but the gravity it matters when the particle rests before the laser comes.
It's still dominated by surface tension.
Before the laser coming. When you do you need to spread the particles, on the surface. Do you use gravity there?
Okay, I get your question. The problem is actually there's like a different, let's say, phenomena that we are not considering, which is even worse, because usually when you run this process, they are in an ambient chamber where you have like a gas flow to remove all the dust. So what Daniel was considering with like all the vapor particles, you have like a surface gas flow removing all the particles. And basically this gas flow also shifts the powder. So actually it shifts the powder even worse than just gravity, and we don't include this because computing this gas flow on top of the surface, you know, hear me complaining about laser ray, you know, and then they ask us, oh, can you also include the gas flow? We're like, no. We should, yes, it would be better to do so. The gas flow is actually even worse than gravity.
I think I frequently hear the word nightmare worse. Okay. Okay, thank you.
Okay. Any other questions? No. I'll go one. Okay, so regarding the coupling. So basically you solve density equation, solve linear moment equation, solve total energy equation. Okay, for both speakers.
Okay.
And then from the total energy equation, I presume that you need to have some relation to get a temperature, and then this temperature will affect the constitutive model. And is it only affect the pressure, the volumetric rather than the devatoric, or actually affect the both this temperature? Because now you got a massive temperature variation, and clearly now the equation of states should be modified accordingly or appropriately according to this temperature variation. Is it dominated by the volumetric, or actually you need to consider both, devatoric and volumetric, to evaluate the stresses?
We didn't check, to be honest.
Okay. What about that?
Same for me. to be
Okay,
honest.
because in Daniel's presentation, I can see that because you say the pressure depends on the density depends on the temperature. And then the divatoric, you keep as divatoric tau, the stresses that you got there. So clearly in your simulation, the temperature will only go to the volumetric. Yeah, the question is why is it just for the simplification or really physically that the pressure will be affected by the temperature rather than the shear?
Okay, we didn't get into it. We have to think about it. It's a good question.
I'm not sure if I get your question right, but you are like going to this volumetric expansion, like this reference density, this temperature-dependent reference density in the stiff equation of state.
Yeah.
Yeah, it's like an approach to account for this thermal expansion, but it's, yeah, as you mentioned before, we're not sure if it's 100% physical, because it's like only, yeah, like inside like this equation of state. Yes, but basically you can simulate it, this thermal expansion effect.
Yeah.
But yeah, we tried also to use like a more physical model for it, but we couldn't get this run basically. And this stiff equation of state was just a very easy solution to also consider those effects of like this volume expansion inside the simulation.
Okay, perfect. Right, thank you. Yeah, any other questions? We have 1 minute left. Oh, according to no. Yeah,
thank you.
Okay, so if not, then I'll close the session now. All right, sorry. Thanks for coming, everyone. Right, thanks for two speakers.
Thank you.
Cheers, guys. Thank you. Bye-bye.
Thank you. Bye.
Thank you. Bye.
Bye.